take a second right now and just, look down at the clothes you're wearing.
Right, like really look at the fabric itself.
Yeah, exactly. The way the individual threads interlace, the pattern, the colors. I mean, we completely take for granted that we can just throw on a complex patterned garment every single morning.
Oh, for sure. We don't even think about it.
But the fundamental technology behind those exact clothes, specifically how they were woven and, the patterns they hold, that can actually be traced back directly to a catastrophic fire in Spain over 3,500 years ago.
Which is just wild because it's a really rare situation in archaeology where a destructive event, like a massive fire, actually acts as a preservation mechanism.
A prehistoric pause button, basically.
Exactly. We're looking at a moment where the ancient past was essentially flash frozen. So it gives us a complete mechanical picture rather than just, a bunch of scattered fragments.
Well, welcome to today's deep dive. Our mission today is to explore how this miraculously preserved archaeological site is just completely rewriting our understanding of prehistoric fashion and engineering and honestly just daily life.
It really changes the whole paradigm.
It does. And we're pulling from a super fascinating stack of sources for this. We've got a fresh 2026 research article from the journal Antiquity, a summary piece from ScienceX, and the official press release from the University of Granada.
And together, they detail a society that was just right on the brink of a major technological leap.
So to really wrap our heads around the stakes of this discovery, we have to look at what usually survives from prehistoric times, which is not much, right?
Right. Almost nothing wooden makes it. I mean, wood rots, organic fibers disintegrate. So researchers are generally left trying to infer these super complex technologies from, scattered durable pieces, like stone or baked clay.
Just guessing how the puzzle fits together without the picture on the box.
Pretty much. But because of this highly specific, sealed archaeological context, we aren't just looking at isolated tools here. We actually have the remains of an entire Bronze Age machine.
Which is just incredible. So to see this machine, we have to visit the specific day it was destroyed and kind of step into the exact environment where it was found.
Let's set the scene.
Okay, so we are at a Bronze Age settlement called Cabezo Redondo. It sits on a terraced hill near Villena in Alicante, which is in southeast Spain.
And researchers were actually able to pinpoint the exact timeline of this destruction with remarkable precision. They used radiocarbon dating.
Right, but they focused on two very specific organic items found in the wreckage, right?
Yeah, so they found a single wheat seed on the street floor and a piece of plant fiber from a rope on a raised platform, and the dates from both of those items matched perfectly.
Wow.
Placing the destructive fire roughly between 1507 and 1428 BC. So about 3,205 years ago.
I gotta say, I always wonder about the precision of those dates. How does a single wheat seed and a piece of rope give us a tighter timeline than, say, dating the massive wooden beams of the houses themselves?
Oh, that's a great question. It comes down to what archaeologists call the old wood problem.
The old wood problem.
Yeah, because if you radiocarbon date a massive pine beam, you might be dating the center of a tree that lived for hundreds of years before it was ever even cut down.
Oh, I see. Or like a beam that was reused for generations.
Exactly. But a wheat seed and a piece of grass rope, those are short-lived. I mean, they grew, they were harvested, and they burned within a very tight window.
That makes total sense.
Yeah.
So when those two distinct short-lived samples give you the exact same date, you know you were looking at a specific unified event in time.
Right, not just a gradual accumulation of trash over a century.
Okay, so picture this. You're standing in what the researchers call a circulation area, which is essentially a gently sloping outdoor street.
Right out in the open.
Yeah, and on a raised platform made of stone and mud, there is this unbelievable assemblage of artifacts. The archaeologists found 49 cylindrical clay loom weights with holes in the middle.
Along with charred timbers of Aleppo pine.
And charred ropes and mats made of Esparto grass.
And honestly, the relationship between all these elements is what changes the game. I mean, finding baked clay weights is super common. They're durable. They survive millennia.
Sure, they're basically rocks.
Right. But finding the Aleppo pine timbers specifically, these timbers they designated as 6 and 7 acting as vertical uprights, with others as horizontal crossbeams, and finding them physically tied together with Esparto grass ropes.
That gives us the literal skeleton of this technology.
Exactly. It operates like a prehistoric pause button.
Or like a mini Pompeii for Bronze Age tech. And the irony here is wild. A fire is the absolute last thing you would ever want near a wooden machine tied together with dry grass ropes.
Oh, it's a total paradox.
Right. But in this specific instance, The fire charred the Aleppo pine uprights and the Esparto grass just enough to carbonize them. The burning structure collapsed, sealing the loom in an oxygen-deprived layer.
So the wood wouldn't turn completely to ash and just blow away in the wind.
Exactly. The disaster that destroyed this loom is literally the only reason it survived for us to find it.
And that paradox of preservation is what allowed researchers to move way beyond merely cataloging artifacts. They were actually able to take this preserved configuration and reverse engineer the actual mechanics of the loom.
Okay, so let's get into that. We have this pile of burnt pine in clay cylinders. How do researchers translate that wreckage into the literal mechanics of prehistoric weaving?
Well, the team used methods developed by the Center for Textile Research at the University of Copenhagen. They wanted to calculate the exact functional capabilities of this loom.
And the key was the physical properties of those clay weights, right?
Yeah, the archaeologists identified these as type 1 loom weights. And what's crucial is that they were unusually light and thin for this region during the Bronze Age.
Because normally the weights found in these contexts are massive. We're talking 400 to 900 grams.
Like hanging small boulders off your loom.
Right. But these type 1 weights were delicate. They weighed only about 200 grams each, and they measured just 40 to 47 millimeters thick.
And that thickness, or rather the thinness, dictates the physical limits of the fabric. So on a warp-weighted loom, the vertical threads, the warp hang down, and are tied to these clay weights to keep them taut.
While the horizontal threads, the weft, are woven through them.
Exactly. So the researchers calculated that to maintain structural integrity, each 200-gram weight could hold between 13 and 20 warp threads.
Okay, let me do the math on that. So that puts every single delicate thread under a highly specific tension of about, 12.5 to 15 grams?
Spot on.
That is wild. I mean, if you think about these loom weights like pixels on a screen, the mechanics really start to make sense.
Oh, I like that analogy. How so?
Well, heavy, thick weights force the vertical threads to be spaced further apart, right? So it creates a low-resolution, blocky, kind of loose fabric.
Right.
But because these specific weights were only 40-ish millimeters thick, the weavers could pack a lot more of them side by side on the loom frame.
Oh, absolutely.
Thinner weights mean you can pack more threads into the exact same physical space, which gives you a much higher resolution, finer fabric.
That's a great way to look at it. And arranging these weights in 2 rows of 22 allowed the weavers to produce a fabric about 1 meter wide.
With a thread density of 5 to 10 threads per centimeter?
Exactly.
Okay, but I need to push back on something here.
Go for it.
When we talk about 12.5 grams of tension and, precise thread density, it makes it sound like these ancient weavers were standing at a chalkboard doing complex physics equations.
Right, in lab coats.
Yeah. Isn't it more likely they just kept hanging rocks on strings until the threads stopped snapping? Just like pure trial and error?
Well, yes, it is absolutely the result of generational trial and error. But that iterative process ultimately achieves highly calibrated engineering.
Okay, that's fair.
I mean, they might not have used modern mathematical formulas, but they intuitively understood the physics of their materials. The threads they were working with were estimated to be less than half a millimeter thick.
Less than half a millimeter.
Yeah. If the tension was off by even a fraction, the threads would snap, or the fabric would warp and just become useless.
Wow.
So the sheer uniformity of the 49 weights found on that platform proves they had moved way past trial and error into a standardized, highly refined manufacturing process.
Okay, so we have this highly calibrated, high-resolution machine, but you don't build a machine that's perfectly tuned just to weave the exact same basic tunics the region had been making for centuries.
No, definitely not.
They were gearing up for a completely new material. And this brings us to what the sources highlight as a massive textile revolution.
Right, so going back through the Neolithic and into the Bronze Age in Iberia, weavers predominantly produced tabby weaves.
Tabby weaves.
Yeah, that's the standard, simple over-under pattern.
Yeah.
And the primary material they used was flax, which is a plant fiber that gives us linen.
But this machine at Cabezo Redondo wasn't limited to a basic tabby weave. Because they had a massive concentration of those lighter, thinner loom weights, they could configure the loom in a completely different way.
Right. The researchers realized this loom could actually be set up with 4 rows of 11 weights, rather than just 2 rows.
And a 4th row configuration fundamentally changes the geometry of the fabric, doesn't it?
It changes everything. It allows weavers to create a twill weave. So instead of a simple over-under, a twill is an over-2, under-2 pattern or variations of that.
Which creates a denser, stronger, more complex fabric.
Exactly. I mean, the diagonal lines you see on a modern pair of denim jeans, that is a classic example of a twill weave.
Okay, but I am trying to visualize the jump from flax to this new material
Mhm.
because alongside the loom, researchers also found new types of clay spindle whorls, right?
Right, the tools used for spinning the raw fiber into thread.
Yeah. And instead of the heavy, flat, discoid shapes they usually use for spinning thick plant fibers like flax, they found new spherical and biconical shapes.
Which is a huge clue.
But mechanically, I'm trying to picture this. I can visualize the heavy, flat disc for flax. But what is a biconical shape? And why does a new material require a completely different spinning tool?
Okay, so a spindle whorl is essentially a weight on a stick used to twist fibers into thread. Flax fibers are long, they're tough, and they're heavy.
Right.
To spin them, you need a heavy, flat, disc-shaped weight to maintain slow, steady momentum without breaking those long plant fibers.
Okay.
But the researchers believe these new spherical and biconical shapes, which look somewhat like two cones joined at their bases, kind of like a spinning top, they point to the adoption of wool.
So wool behaves completely differently than plant fiber.
Fundamentally differently. Wool fibers are short, light, and springy. If you use a heavy flax spindle on wool, it'll just snap the short fibers right apart.
Oh, so you need a lighter biconical shape that concentrates the weight near the center of the spinning axis.
You got it. That allows the spindle to rotate much faster, rapidly twisting those short, springy wool fibers into a continuous strong thread before they can pull apart.
Okay, so the combination of the light loom weights, the potential for a 4-row twill setup, and the biconical spindle whorls, all of this signals a massive shift to wool.
A total revolution.
But why make the jump? I mean, if they were already successfully making clothes out of flax using a reliable tabby weave, why go through the trouble of inventing a much more complicated 4-row machine and entirely new spinning tools?
One word. Dye.
Dye, like colors.
Yep. Wool is significantly easier to dye than plant fibers like flax. Flax stubbornly resists holding color. So when you combine easily dyed wool with a complex twill weave, weavers are no longer just producing blank utilitarian canvases.
Learn to art.
Exactly. They can weave intricate, multicolored pattern designs directly into the structure of the cloth. Chevrons, diamonds, stripes. They're creating actual fashion.
Wow. It's like having a perfectly reliable black and white printer that does the job fine and then upgrading to a highly complex color printer.
That's the perfect analogy.
They wanted patterns, they wanted colors, so they completely re-engineered their technology from the spindle whorls all the way up to the loom structure just to make it happen.
And the lead author of the study, Dr. Ricardo E. Basso-Real, noted that this discovery allows us to see the loom frozen at the exact moment it was in use.
Which is so rare.
It is. And to contextualize the timeline here, twill weaves did not become widespread in Europe until the beginning of the first millennium BC.
Wow.
But the setup at Cabezo Redondo sits in the mid-second millennium BC, making it a remarkably early, cutting-edge hub for this whole textile revolution.
So we have this cutting-edge, highly engineered machine producing revolutionary colored fabrics. The next layer to explore here is who was actually operating this technology and where it was located within the village.
Right, the social aspect.
Because the physical location of this loom tells a story just as compelling as the mechanics.
Oh, absolutely. See, the loom was not found hidden away in some specialized, isolated workshop. It was situated on a shared exterior platform that physically connected two different houses.
Houses designated as House 32 and House 34, right?
Yep. And the archaeological record even gave us a footprint of the workspace itself.
Oh, right, the grass mat.
Yeah. A plated Esparto grass mat was found stuck to the bottom of one of the loom weights, showing us exactly what the weavers were standing or sitting on while they worked.
That is wild. We know exactly where they stood. And that physical footprint indicates weaving was a cooperative, decentralized domestic activity.
Right. It was carried out by household groups sharing an outdoor communal space right between their residences.
I mean, think about the layout of your own modern life. There is a stark difference between a communal office kitchen where everyone is chatting, making coffee, and sharing space versus, say, a locked, climate-controlled server room where only a few specialists have access.
That's a really good way to put it.
Because in the Bronze Age, crafts like metallurgy or working with ivory or crafting gold jewelry, those were the locked server rooms.
Oh, highly restricted.
Right. They were highly specialized, tightly controlled, often dangerous because of the heat, and relegated to non-residential, isolated areas of a settlement.
But the contrast here is striking because this loom represents arguably the most sophisticated revolutionary technology of its time, capable of complex twill weaving. Yet it was operated at the ancient equivalent of the water cooler,
Fully embedded in everyday domestic life.
positioned in the open air, surrounded by neighbors, daily chores, and family interaction.
The most advanced technology of the era was just sitting on the back porch between two houses.
Literally. And this decentralized approach to production had massive implications for the social fabric of the settlement. Because textile production was a domestic activity rather than an isolated guild secret, it empowered a wide variety of
That
people.
wasn't hoarded knowledge.
Exactly. The researchers noted that loom weights were found across 16 different spaces at Cabezo Redondo. This was a massive community-wide industry engaging multiple households in this technological revolution.
That completely shifts the traditional image of the Bronze Age for me. Instead of focusing solely on, solitary blacksmiths forging weapons in isolated huts, we see an entire community cooperating in the daylight, engineering colorful, complex garments together on their shared patios.
It is a profound adjustment to our historical perspective, and it was made possible entirely by archaeologists meticulously analyzing the spatial distribution of charred wood and baked clay.
So let's retrace the path of this deep dive. We started with a catastrophic fire 3,500 years ago that collapsed a structure in southeast Spain.
Right.
Because the fire starved the wood of oxygen, it charred the Aleppo pine timbers and Esparto grass ropes rather than turning them to ash.
The prehistoric pause button.
Exactly. And by analyzing those preserved timbers and a collection of unusually thin 200-gram clay weights, researchers were able to reverse engineer the precise tension and thread density of a Bronze Age loom.
Calculating that exact 12.5 to 15 grams of tension.
Right. And through that, we discovered a community transitioning from simple flax to complex, dyed wool twills, using those biconical spindle whorls to spin the springy fibers.
The textile revolution.
And most surprisingly, they were operating this cutting-edge technology out in the open as a cooperative, community-wide industry embedded in their daily domestic lives.
I mean, the preservation of this site is an absolute triumph. But, it also highlights a concept that kind of shadows all archaeological interpretation.
What's that?
Survival bias. This intricate window into Bronze Age innovation exists only because of random chance.
Wow. Yeah.
A fire happened to char the wood perfectly, and the clay weights were already baked to survive the heat. If that loom had been dismantled naturally, or if the weights had been made of unbaked mud or wood, we would have zero evidence that this sophisticated four-row tool technology ever existed at Cabezo Redondo.
We just think there's some making basic flax tunics.
Exactly. It really forces a look at our own era. Consider the foundational technologies of your modern life right now. So much of our world is built on fragile plastics that degrade, digital data stored on volatile servers, and synthetic materials that will either vanish or warp beyond recognition.
That's honestly terrifying.
In 3,500 years, will future archaeologists completely misunderstand the complexities of our daily lives simply because our modern looms weren't made of fire-baked clay?
It is a brilliant and honestly slightly unsettling thought. We are leaving behind a digital and plastic footprint that might not survive its own version of the fire.
Something to think about next time you back up your hard drive.
For sure. Thank you for joining us on this deep dive. Next time you pull on a sweater or look closely at the diagonal twill of your jeans, take a second to appreciate the thousands of years of engineering, material science, and communal back porch innovation woven directly into those threads. See you next time.